Hello my dear students, in this video now we are going to study about the preparation and properties of the indole. In indole, two rings are there. One is the 5-membered ring and the other one is the 6-membered ring. 6-membered ring is the benzene and the 5-membered ring is the pyrrole. We know very well that other name for the pyrrole is the azole. Okay, na? So that's why this is also known as 1 comma 2 benzazole, 1 comma 2 benzazole, because here benzene is fused with azole, so that's why we call it as the 1 comma 2 benzazole. Otherwise we can call it as the benzopyrrole. So like this, indole has the two more names, like 1 comma 2 benzazole and benzopyrrole. The preparation of the indole, first of all we study about the medullum synthesis. In medullum synthesis, starting material is the N-formyl orthotolidine. So here formyl group is attached and this is CH3. So look here, if you write CH3 on benzene, that becomes the toluene, and at ortho position imine group is there, so we call it as the orthotolidine, and on N formyl group is there, so that's why its name is N-formyl orthotolidine. So its name is N-formyl orthotolidine. So this is the starting substance, and this is treated with a strong base like potassium tertiary butoxide. Look at this is potassium tertiary butoxide. So it is a strong base. Here it is treated at 330 degrees centigrade to 360 degrees centigrade for the 25 minutes. Then we get the indole. So this is the medullum synthesis. In medullum synthesis, N-formyl orthotolidine is the starting substance. Now we go for the mechanism. We know very well that any alkyl group that is present at alpha position to a double bond shows the acidic nature. So these hydrogens are acidic hydrogen atoms. So that's why when it is treated with the base, hydrogen atoms from here are abstracted and we get a carbon ion. So I am writing CH3 group like this, CH2-H, and I write here N-formyl group. When it is treated with the potassium tertiary butoxide, that means tertiary butoxide ion, now this hydrogen will be abstracted here and we get a carbon ion. Okay, now this carbon ion attacks on this carbonyl group, and as a result cyclization takes place. O minus and H. So this tertiary butoxide here goes as the tertiary butyl alkoxide, tertiary butyl alcohol. So this oxide abstracts the hydrogen from the tertiary butyl alcohol and changes into the hydroxy group. Still, two more hydrogens are there, and these are alpha hydrogens to this double bond. No? So, in the presence of the butoxide anion, these hydrogens are abstracted here, and this electron shifts here, and this hydroxide ion goes outside. So, as a result, on the whole, water molecule goes outside, and the indole will be formed like this. So, like this, we get the indole in medullum synthesis. Now we study the second preparation method of the indole, that is the research synthesis. In a research synthesis, we use the two starting materials. One is the orthonitrotoluene. So look here, this is toluene, and at ortho position we are writing the nitro group. So it becomes the orthonitrotoluene. So this is orthonitrotoluene, and we use the ethyl oxalate as the another starting material. So it is diethyl oxalate or ethyl oxalate. Okay. In the first of all, we treat this with the base. So here also we are using the potassium tertiary beta oxide A base, and then after the product formed is treated with the what is that a reducing agent, that is the ferrous sulfide or zinc or acetic acid mixture. So as a result, what happens means we get the indole. Now we go for the mechanism of this reaction. As we have already learned that the alkyl group that are present in the alpha position to double bond are acidic in nature, no? So as these hydrogens are acidic in nature, these are abstracted by the strong base like tertiary butoxide. So for convenience, I write the methyl group like this. Now, tertiary butyl alcohol goes outside, okay, and we get the carbon ion. This is the first step. In the second step, this carbon ion attacks on the ethyl oxalate. For convenience, I write the ethyl oxalate like this. Okay, the carbon ion attacks here, and the double bond shifts onto this one. As a result, we get the oxide anion. CH2, and I write this C here, so O minus OET and COOET, and I write NO2 group here. Okay, so from tertiary butyl alcohol, this one abstract the hydrogen and changes into the hydroxy group. I write NO2 here and CH2 OH, sorry. So this ethoxy group is a easily leaving group. As a result, what happens? This electron pair shifts here. As a result, this ethoxy group outside. So as a result, we get the keto once again, and this ester group is present like that only, and so this is the product obtained in the second step. In the third step, this is treated with the reducing agent like ferrous sulfide or zinc acetic acid mixture. On treating with ferrous sulfide is a reducing agent. In ferrous sulfide, ferrous ions are there, and we know very well that ferric ions are more stable than the ferrous ions. As a result, ferrous ions easily convert into the ferric ions. As a result, ferrous ions act as a reducing agents. So we can use this one, or we can use the zinc and acetic acid mixture as the reducing agent. So when we treat this with reducing agent, this nitro group changes into the amine group. So it changes into the amine, and one electron pair is there on the nitrogen of the amine. Now now what happens means this electron pair is given to here. As a result, this bond breaks and negative charge appears here. As a result, cyclization takes place. Here positive charge appears on the nitrogen atom and negative charge appears on the oxygen atom. Next what happens means this electron pair is given to here, and this hydrogen attacks on this oxygen. As a result, we get the hydroxy group here. By the next movement, in the fourth step what happens means, I write here. In the acidic medium or in the basic medium, this water molecule goes outside. So water goes outside and we get the indole product. So it is a product of ethyl product of indole to carboxylic acid. So it is known as the ethyl indole to carboxylate. But here to get the indole we have to remove this one. To remove that one, what we have to do means we have to hydrolyze that one. So when we hydrolyze this ester, in the presence of base or acid, this one undergoes hydrolysis and we get the indole to carboxylic acid. Indole to carboxylic acid like this. And on heating, this CO2 goes outside and we get the indole. We get the indole like this. So this is all about the research synthesis. Now we go for the third preparation method of the indole, that is the Fischer indole synthesis. This is very important for the examination point of view. In Fischer indole synthesis, we use the two starting substances. One is the phenylhydrazine and other one is the aldehyde or ketone. Here we are using the estophenone. Depending on the aldehyde or ketone that we use, we get the different products. So first of all, what happens means we get a condensed product. We go for the mechanism afterwards. First of all, we take the product here. Look here. So as we are taking the estophenone here as the starting material, we get the 2-phenyl indole as the product. So look here, this is the 2-phenyl indole. Okay, now we go for the mechanism. Go for the mechanism related to the Fischer indole synthesis. In the Fischer indole synthesis, first step is the condensation of the hydrazine with the carbonyl group. So here as a carbonyl group we are taking the acetophenone. This is acetophenone. So on heating, condensation takes place and the water molecule goes from these two compounds. So as a result, we get the condensed product. CH3 and pH. So this alkyl group, that means methyl group, is in the alpha position to this double bond. So this may undergo tautomerism and we get this product. So during the tautomerism, what happens? The hydrogen CH hydrogen bond breaks here and it changes in double bond, and this electron pair shifts onto this nitrogen. As a result, this nitrogen becomes the NH group, and we get double bond between these two carbons. Okay, so consider this as the product 1. Okay, and in the second step, this product 1 is treated with the acids. We know very well that acids contain H plus ions in them. No? So when this one treated with the acids, what happens? The nitrogen gets the hydrogen ions. That means it will be protonated, and as a result, positive charge appears on the nitrogen atom. Now the positive charge that appears on the nitrogen atom becomes the driving force for the cyclization. So look here, to balance this one, what happens? This bond shifts here, and to balance this one, this bond breaks and shifts here, and next moment, by the next moment, what happens? This bond breaks and is shifted to here. As a result, cyclization bond will be formed between this carbon and this carbon. So we get here N double bond H and one hydrogen is here, and bond is formed between carbon of the benzene and carbon of the carbonyl group. NH2 plus and one phenyl group is also there, no? And now we know very well that the positive charge is the driving force, no? So now this bond breaks here, and electron pair shifts onto this nitrogen. Then positive charge appears here. To balance that one, what happens? The electron pair shifts here, and to balance, and as a result, positive charge appears on this carbon. To balance that one, what happens? This bond breaks and bond will be shifted here. As a result, we get cyclization occurs and we get this product. Look here. NH2 and pH. And in the next step, what happens means ammonia goes outside in the presence of the acids, and what happens? We get the indole product. We can write as the we can write this step as the another step, but here I am writing in the second step only. So look here, like this we get the product of the indole. So this is a 2-phenyl indole. So this is Fischer indole synthesis. In Fischer indole synthesis, starting substances are two: phenyl hydrazine and the carbonyl compound. Depending on the carbonyl compound, we get the different indole derivatives. For the fourth preparation method of the indole, that is the Bischler indole synthesis. In Bischler indole synthesis, we use the two starting substances. One is the aniline. So this is aniline, and second one is the alpha halo aldehyde or ketone. So look here, here we take one ketone, so this is acetone, and if you write one bromine or chlorine here, that becomes the alpha bromoacetone. So this is alpha bromoacetone. Okay, so here we get the indole. And depending on the structure of the ketone, we get the different indole derivatives. As we are having CH3 here, we get the CH3 in the third position. So it is what is that? 3-methyl indole. Now we go for the mechanism. mechanism. We know very well that amine group and hydrox group easily react with the halogen compounds. No, so in the first step, what happens means this alpha bromo aldehyde or ketone. That means not only alpha bromo, alpha keto, alpha halo ketones easily react with these amines, and we get a substituted product, substituted anions. Double bond O and CH3. So this is the product obtained in the first step, and this product is treated with the acid in the second step. So when this is treated with the acids, this carbonyl group will be protonated, and as a result we get the carbonium ion. So it becomes oxonium ion in the first step, then it changes into the carbonium ion. Now this positive charge behaves as the driving force for the cyclization. So to balance this one, what happens? This bond shifts here and cyclation occurs, and to nullify that one, this electron pair shifts here. As a result, we get this product. Now here we have the hydrox group as well as the methyl group, and we have the positive charge here and one hydrogen here. In the next moment, what happens? This bond breaks and this electron pair shifts here. As a result, the H plus ion goes outside. This H plus ion may attack here also. As a result, what happens? Look here. This may changes into the oxonium ion like this. Sorry, here we have methyl group, and we are having the hydrogen atoms. No, so I write one hydrogen here. So what happens in the next moment? This one breaks here and this one goes outside. As a result, we get the indole derivative. So this is what is that 3-methyl indole. So like that, depending on the structure of the ketone that we take, we get the different indole. What is that? Different indole products. Now we discuss about the reactivity and properties of the indole. We know very well that indole is an aromatic compound because it follows the Huckel rule. In indole, we have the pyrrole ring as well as the benzene ring. Here in pyrrole, 9 atoms are there in the 2 cycles. Look here, 6 carbon atoms in benzene ring, 2 carbon atoms in pyrrole ring, and 1 nitrogen atom. That means here in indole we are having the 9 atoms, but here we have the 10 5 electrons. Look here, 1, 2, 3, 4, and 1 electron pair is there here. No, so this also involves in the aromatization. So that's why we take it as the 10 electrons. So here in indole we are having the 9 atoms in the ring and 10 electrons in the ring. So we can consider it as the 5 excessive compound, whereas simple benzene ring is 5 sufficient compound. Indole is 5 excessive compound. That means here indole is more reactive than the benzene towards the electrophilic substitution reactions, and compared to the benzene ring, pyrrole is 5-excess compound. Among these two, look here, among this benzene and pyrrole ring, pyrrole is more active towards the electrophilic substitution reactions, because in between these two, pyrrole is 5-excess compound. Okay, so when this indole is subjected to electrophilic substitution, electrophile will be substituted in the pyrrole ring rather than in the benzene ring. And again, we have to understand at which position, either at alpha position or at beta position, at which position the electrophile substitution takes place. To understand that one, we have to take the resonance structures of these substituted products. Look here, when electrophile attacks on the alpha position, then what happens, benzene structure will be disturbed like this. Look here, we get positive charge here, and to nullify that one, this bond pair shifts here. As a result, carbon of the benzene ring is a positive charge. That means the benzene ring structure will be disturbed here. But when the electrophile attacks on the beta position, there will be no disturbance in the structure of the benzene ring. So by these structures we can say that in indole, electrophile will be substituted at beta position of the pyrrole ring, beta position of the pyrrole ring. And we have to understand that as it is the 5 excessive compound, mild conditions are required for the electrophilic substitution reactions. Now here we take some example for the electrophilic substitution reactions. First one is acetylation or acetylation. If acetylation is carried out in the presence of acetic acid, we get 3-acetyl indole. And if acetylation is carried out in the presence of the sodium acetate salt, we get the N-acetyl indole. And chlorination with sulfonyl chloride, we get the 3-chloroindole. And bromination with bromine in the presence of ethyl alcohol, we get the 3-bromoindole. And iodine in the presence of acetic acid gives us the 3-iodoindole. And look here, for nitration we don't require the nitration mixture. Here we have to take nitronium benzoate because this is mild nitrating agent. We get the 3-nitroindole. And in sulfonation there is no need to take the oleum or concentrated sulfuric acid, just we have to take the sulfur trioxide gas. We get the indole 3 sulfonic acid. And a Reamer-Tiemann reaction. In Reamer-Tiemann reaction, we get the indole 3 carbaldehyde. In the similar way, in Wills-Meyer reaction also we get the indole 3 carbaldehyde. In Reamer-Tiemann reaction, it is treated with the chloroform in the presence of base. In Wills-Meyer reaction, indole is treated with the N-dimethyl formamide in the presence of the phosphoryl chloride, that is POCl3. And this indole also undergoes azo coupling, and we get the 3-phenyl azoindole. And this also shows the Mannich reaction. In Mannich reaction, indole reacts with the formaldehyde and the secondary amine, and we get the 3-N-dimethyl iminomethyl indole. So these are some electrophilic substitution reactions exhibited by the indole. Electrophilic substitution reactions exhibited by the indole.